for parts of Oklahoma, Kansas, Missouri, and Arkansas. By 4:30 p.m., storms began to rise over Kansas. Meteorologists at the National Weather Service watched them intensify on radar. At 5:09 p.m., they issued a tornado warning for an area just north of Joplin. At 5:17 p.m., they issued a warning for Joplin itself. 17 minutes later, a mile-wide tornado was headed into Joplin. A high-density signal appeared on the radar. A huge swirling mass of debris had been lifted from the ground and was being held aloft by the tornado. In the aftermath, Joplin residents emerged to find whole blocks scoured by winds up to 200 miles per hour. Buildings and houses destroyed. Lives lost and neighborhoods torn apart. The scale of destruction led to an unprecedented effort to find out exactly what happened here and whether similar disasters could be prevented in the future. Joplin may well be a watershed event in a growing clash of people and weather, especially in tornado-prone sections of the southern Great Plains and the southeast. From its start as a mining center and regional crossroads in the 19th century, Joplin has grown into a small city with just over 50,000 people. Its population expands outward from a central district at the meeting of Highways 43 and 66. Joplin is part of a larger trend. As the U.S. population has grown over the years, it has concentrated more and more in urban areas, often with extended suburban footprints. So when a tornado touches down, the targets are larger and more concentrated, with a greater potential for large-scale disasters. The National Weather Service is responding with powerful technologies. Satellites that allow forecasters to monitor storm systems across the continent. A network of Doppler radars that can map swirling motions within the clouds and identify early signs of dangerous weather. And computer models that predict weather conditions hours in advance. To increase the precision of these forecast models, researchers have been going into the field to study storms up close. Their observations are helping scientists to hone new generation models that can recreate the rise and fall of thunderstorms in unprecedented detail. These models bring together theories of how clouds form, how winds, temperature, pressure, moisture vary with altitude, the effects of rain and hail, the influence of the jet stream overhead, and a host of other factors. They put these models to the test with a strong storm that occurred just 2 days after Joplin on May 24, 2011. This time over central Oklahoma. Another mile-wide tornado cut a path 63 miles long near the town of El Reno. Because of the power and longevity of this tornado, scientists sought to reproduce it in one of the world's largest supercomputers. They set their virtual atmosphere in motion, starting with conditions measured that afternoon. A large thunderstorm rises into the upper atmosphere. Strong high-altitude winds push the cloud tops out ahead. The wind, moving into and around the storm, shifts direction and speed with height. That causes the storm to rotate. The cloud base lowers as warm, moist air condenses as it streams into the storm at ground level. It's a familiar sight in tornado country. Darkness envelops the land, the view obscured by sheets of rain or hail. The ominous shape of a tornado looms ahead. Scientists position themselves at safe distances to take a variety of atmospheric readings. Or to track the flow of clouds and rain using mobile radars. One advantage of simulating the storm in the lab is that the scientists can track the wind, rain, ice, and clouds in 3 dimensions, from its initial formation all the way to its eventual decay. Here is a cross-section of the virtual El Reno storm, just above ground level, early in its life. The red and orange patterns indicate sheets of falling rain, much like the images picked up by weather radars. On the forward part of the storm, the rain produces cool downdrafts that undercut warm air flowing into the center of the frame. In this area, along the boundary of warm and cold, scientists release a series of virtual streamers. They show that the air is spinning horizontally, then vertically, as it rises into the updraft. This causes the storm to spin at lower altitudes. In real life, the lower portion of the storm takes on the ominous form of a rotating thunderstorm called a mesocyclone. Something more is needed to produce a tornado. As the virtual storm gains strength,